First, I'd like to thank everybody for this wonderful award. It's a tremendous honor. Totally unexpected. I didn't even know this award existed. I was told that traditionally, people who get this award talk about their careers and stuff, and I'll do that. But I want to talk about interesting stuff too. So what I'll do is I'll spend like about 10 minutes or so talking about some of the projects I've been involved in my career. Just spend a little bit of time on that. But I'll spend most of my time moving on my latest projects, which probably be my last ones in the Weather Service, last big ones anyway, which would be I participated as the lead author and lead investigator on the Joplin Service Assessment. This is a before and after in Joplin. Pretty impressive picture there. And one of the leaders of the Impactbased warning tornado warning project, which is ongoing in the Weather Service right now. So I'll spend some time talking about that. I guess I owe an explanation as it's titled, don't I? Diagnosing tornado fever. I should let Greg.
This is your talk.
Tornado fever is not, and I'll just briefly, I don't want to get ahead of myself here, but tornado fever is something that we kind of coined. Rich too. We talk about it in the office all the time. It's not about crazy storm chasers and stuff like that. It's more about this infatuation that a lot of meteorologists have about tornadoes, and a lot of times that's what brings them into the field. And it kind of buys into this myth that all tornadoes are these bloodthirsty killers, but they're really not. Only a few of them are. Most of them are pretty small, short-lived, weak. They're no more damaging than your basic severe thunderstorm. So what we're trying to do with the IBW project is put an emphasis on the killer tornadoes. But along the way, we run into a lot of resistance just because people think that all tornadoes are bloodthirsty killers. And so it's been a challenge for us to kind of move ahead. A lot of people, like I say, they're infatuated with tornadoes, and they don't want people to mess with their tornado warnings. And it's mostly within the field of meteorology. Our customers that we've talked to, emergency managers, they're fine with changing. They think it's a great idea, but we have resistance within the field itself. And so that's been interesting. So before I move on, I'm required to do one thing. I have to read this. I've been talking to lawyers today. I have to say, in order to avoid any appearance of government endorsement, I should state that my opinions are mine alone and do not represent the views of the Department of Commerce. See Department of Administrative Order 219-1, Section 11. So, Lynn and I moved to, shortly after walking out of these doors in 1982, we moved to Little Rock, Arkansas, where I started my career in the Weather Service. And great place to start a career. I learned a lot about radar meteorology. It was a big deal there. Operational meteorology. And by the time I was working solo on the radar, and this was one of the very first times that I worked solo on the radar, this happened. And this is the Greers Ferry Lake, Arkansas bridge, and an F4 tornado on my watch came down there and dumped the bridge in the water. This was pretty common back then. We had a severe thunderstorm warning out in effect. I had a severe thunderstorm warning out in effect. And didn't issue the tornado warning until after we got the reports of the tornado, and it was passed at this point. So, and then we moved back to Michigan shortly after that. But the reason I wanted to have this up here was, sometimes these little seminal moments happen early in a career that can really have an impact on you, and which way you go in your career is very dependent on your attitude toward it. Some people kind of get shy away from it. In my case, I made a point of really ratcheting up my focus on self-learning and really working hard at that. Equally as important, working on trying to learn how to apply academic principles, things I learned here, into an operational environment. That's not an easy thing to do. And Greg can attest to that. He has to teach that. And the other thing I learned was don't be afraid to take risks. And that's what often happens when somebody is faced with, a failure. They become a little bit gun shy. And I taught myself not to do that. And that was a characteristic that served me well during my career. If you're in the prediction business, you're going to deal with risk. If you can't deal with it, you shouldn't do it. Oh, we'll go back real quick here. What's on the lower left here is, right after this happened, I started a study, which was later published in National Weather Digest. And this is just a relational climatology relating height of the freezing level to the height of the 50 to 55 dBz echo. And this is for hail occurrence versus no hail occurrence. So that was one of the first studies that I'm aware of that actually normalized these radar signatures to environmental conditions. And this principle is still in use today. So we did move back to Michigan. And I can tell you, forecasting in Michigan is much harder than in the Mid-South. Very challenging. Winter weather especially, aviation. FAA keeps aviation bad weather scores. Pellston Airport's has the worst aviation weather in the country. And I can vouch for that. But this is how we did, this was our flagship product, how we had it all set up. These are the zone forecast boundaries at that time. And these are based on climatological divisions throughout the state of Michigan. But we had problems with fitting this to actual weather. For example, lake effect in particular, you can see this zone 17, which extends from here to here. Northwest flow had heavy lake effect snow in this part of the zone, and it'd be sunny over in here. Similarly in zone 16, which covered the straits. Marty remembers this well. We had a lot of problems with that. And Fred Keyes, the lead forecaster there, and Fred, actually, he was a graduate of this department as well. We sat down one day with Marty's help, and we sat there and, okay, how do we redesign these zones to fit lake effect weather patterns a little bit better? And after some miserable attempts at that, we just kind of threw our hands up and said, every county has to be a zone. And so we did that. And so in this manner, we could take weather and we could actually, whatever the weather was, we could have the flexibility to kind of group these counties together. And it really seems simple at the time, but it was a big deal back then. It took a lot to get that implemented. And by 1993, it was implemented nationwide. It was in effect for probably our primary way of doing things for about 10 years. Nowadays, you're more likely to get this is how we do our forecast now. It's on an underlying grid, it's done graphically. The grid was 5 by 5 kilometers, 2.5 by 2.5 now. And so that's how we do it. And you're more likely to get your forecast via a point and click methodology. Here's a grid box there, which kind of shows the area for this forecast. High near 50, that was last weekend.
That was Saturday.
That was Saturday.
Beautiful.
Or getting it through hourly time series, weather graphs like this. You're likely to get your forecast through a private company now, like the Weather Channel. You can get it online there or watch it on TV. So, right about that same time in the late 1980s, I got involved with a forecaster at the Ontario Storm Prediction Center, extraordinary guy, Brian Murphy, who called me up one day and called Tom Nizio, who's my good friend who was at the NWS in Buffalo and now works with Jeff at the Weather Channel. We, exciting stuff going on, operational meteorology at that time. New technology, radars going up, new techniques. We're just getting science and operations officers in all the forecast offices. So we needed a way to kind of share information and tools and techniques that we're developing and across international borders even. So we did the first in 1989, I think it was, or 1990. The first annual U.S.-Canada Great Lakes Operational Meteorology Workshop. And it was only about 15 of us. We had to take annual leave. Marty let us do that and do it on our own time, but we actually did that across the border, and there were like 15 of us that met in a little tiny conference room at Pearson Airport in Toronto. We've done 23 of these since then. Now we typically get, 70 to 100 people at those. We've had it here in this room a couple of times. We've hosted it in Ann Arbor 4 times, I believe. And the last time you can see, we'll have to get a new logo next time. That was in 2014. We held that at the new auditorium in Laurel. So I'm pretty proud of that. That was something that continues on to this day to be a founding member of that workshop. Okay, this is what the observation network across the Great Lakes, the coastal observation network and the buoys looked like back in about 2000, 2003 or so. We had, at the time, NOAA started making a big push for its line offices to start working together. We previously had worked in stovepipes. I guess we still do to some extent. But Weather Service, for those that aren't aware, Weather Service is a line office for NOAA, National Ocean Service, Office of Oceanic and Atmospheric Research, which is the Great Lakes Environmental Research Lab, NESDIS for satellites, and Fisheries, which has no presence in the Great Lakes whatsoever. But I had the opportunity to co-lead a team to actually kind of make NOAA put their money where their mouth was, and they came through. But we actually went about trying to increase the density of our coastal marine sites in the Great Lakes, which now looks like that. So that's a tremendous accomplishment, I think. A lot of people put a lot of time and effort into, and NOAA probably put $500,000 into that. It's even bigger than that now. This is from 2 years ago, but now we have a few more coastal buoys out here in Lake Michigan and a couple up in Lake Superior. Okay, I'll talk about this a little bit. This one's also a NOAA collaboration effort. This is, of course, this is a wind forecast, a gridded wind forecast for Lake Huron and at Georgian Bay. We're allowed to forecast for the Canadian side. We reciprocate. They can forecast for Georgian Bay too. It's kind of an agreement we have. But you can see these gale force winds up in the northern part of the lake and into Georgian Bay, and the Weather Service produces this forecast. From that, we derive our wave forecast, and NWS is responsible for the wave forecast out here over Lake Huron and all the Great Lakes for that matter. But we're not responsible for the water level forecast. That's another line office. That's the National Ocean Service. And GLERL does work in that area as well. And you can see how this matches up nicely. You know, the wind forecast and the waves, they match up. Water levels are high in the right place and low in the right place. But it wasn't always that way. Because National Ocean Service, for a while, back in the day, would not use the National Weather Service wind forecast in their water level forecast. It was they would use the NAM, which, you know, a lot of times that was okay, but you could run into issues where you'd have a Weather Service would have a forecast like this, and if the NAM took the low south of the lake, you'd have high water levels here in their forecast and low water levels on the other way. So it was on the other side of the lake, so it just wasn't consistent. It's a simple thing to get another line office using the official NOAA wind forecast. How long did we work on that?
A decade. Well, maybe not quite a decade, but.
Yesterday you said your entire career.
That's true. It was the first year I came in at the
Okay. So, but we did, and it's now, it works out pretty well. We actually have everybody on the same page. And like I said, it seems like a simple thing. I laugh about it, but man, was that a lot of work to get that done. I don't know how many of you are aware that the Weather Service was actually pretty involved in weather support for the Enbridge Oil Spill on the Kalamazoo River. I'm sure some of you were. But that was something different for us. We were actually on site for 2 months for the Detroit office and the Grand Rapids office. And well, actually, we had forecasters at the State Emergency Operations Center in Lansing. So these are the things that we provided for them. And this was, like I said, this was new for us. The support was mostly for the state and for the EPA, but we had to provide things like heat forecasts. There were heat concerns out there. You can see workers working on the river here, heavy protective equipment in the middle of summer. So, you know, heat stroke was a real concern. So they needed real detailed temperature forecasts, lightning threats for people working out in the field, severe weather threats. They had trailers out in the field, and we had one event with 70-mile-an-hour winds, I think, Rich. Did we have to evacuate? We evacuated the area, and I think some of the trailers were actually destroyed. So that's the kind of weather support that that is needed. Here's an example here of a windrows. They had airborne chemical impacts, mostly from fumes from the diesel. And I think they had to evacuate some areas just from the smell. So anyway, I co-led the service assessment for that. Weather service assessments are supposedly these internal quality assurance reports. And they're never internal. Everything we do is immediately external. But where we kind of look at what went well, what didn't go well, make recommendations. There's usually a series of findings and what we can do to do better. And those findings and recommendations are implemented. And one of those was that we get more involved in providing this kind of support. We don't actually do this ecosystem forecasting, but we do, as Louis Ussolini says, provide enable and support. And so we started this summer, actually. This is the harmful algal bloom forecast. Ocean Service is responsible for the forecast, and GLERL helps them out. But we provide weather support for them a couple times a week, and they're interested a lot in ranges of possibilities for wind forecasts. And that's what we've been doing. Greg actually developed this ingenious probabilistic windrows right here using ensembles. And I've never seen anything like that before. That's pretty slick. So that gives us an idea. We can actually communicate to NOS what we expect the wind direction to be and give the range of possibilities. Same thing with the speeds. So they find that critical. I'll move on to the fun part of the talk. I had a great opportunity to, my boss in Central Region headquarters at the time, Lynn Maximuk, was actually supposed to visit our office. He was in Cleveland at the time. And he was driving back when this happened. And so he had to cancel his trip to the office, and he calls me up. I wasn't even aware of what happened the previous night. This tornado had occurred. And he says, I can't come to the office. Well, why not? He says, well, don't you know? He tells me, well, over 100 people died in Joplin last night, so he's got to get down there. And his last words for me was, don't go away, I'm going to need you. And so within a day, he calls me up and says, I need you to lead this service assessment. So I got to pick a team of 5 people, including myself. 3 meteorologists, Justin Weaver from the Lubbock, Texas office, Gary Garnett from the Cleveland office. We had 1 social scientist, Jen Spinney, who's at the University of Western Ontario in London, and Bethany Hale, who is a public administration specialist for the Weather Service, and various contributors. There's one right there, and Rich contributed to. We went down to Joplin. We waited about a week. We didn't want to interfere with recovery efforts. But when we got there, we were on site for 5 days, did about 100 interviews. We talked to tornado survivors, the general public, EMs, media, dispatch, fire chief, businesses, schools, city officials, and of course NWS staff. And you can see these are the stats for the tornado right here. You can read that for yourself, but a lot of damage. It was a big deal. And so it was quite a challenge leading that service assessment. And I'll get into some of our findings and recommendations and what we're doing about it in a second. But I'll show you some of the pictures that we took. Devastation was just astounding. This particular picture, I'm standing down on Iowa Avenue, which is running in parallel to the screen here. And probably the biggest density of fatalities occurred right there. You can see I'm looking up a hill, it's Main Street up here. But you can actually see the damage increasing due to vortex stretching in the tornado from the top of the hill to the bottom of the hill. And right behind me is the Joplin High School. Graduation was that day, that afternoon, when the tornado hit. Luckily, the high school wasn't big enough to hold graduation. They moved it to the local college north of town. there would have been, we probably would have doubled the fatalities, if not tripled it. And you can see, the picture is pretty impressive. I can tell you that being there in person is a whole lot different. It's a whole different perspective, and it was a humbling experience to see all that. It was just damage as far as the eye could see. So this is actually looking east. You can see a lot of the damage here. By the time we got there, they cleaned off all the roads, obviously. This is the entrance to the hospital, which was hit and destroyed. Here's the front of Dillon's grocery store. I'm going to show you the back in a minute. There's the Home Depot over here on the upper right. Don't want to be in a big box store when a big tornado hits. And you can see in the lower, you don't want to be in a vehicle either. We saw hundreds of these vehicles like this. Luckily, nobody was in that one. But, you got a real good sense of, vehicles just don't withstand large tornadoes. I do recommend, however, being in a bank vault, if you can get in one. That's the only thing that's standing there. That's right. You can't read the sign here, but it's actually directing customers to another bank location, just in case anybody got in the drive-through here to make a withdrawal. I don't know what that is up there. We never did figure that out. I'm assuming it's a van or a bus or something in the upper right. You see the X's on there. And rescuers are going from place to place. What they do is they put an X on there to denote that they've searched it. And if there's fatalities, they'll put the number of fatalities or injuries. They usually put the date that they searched it, and this one they didn't. Here's a house that's been scoured. Most houses didn't have basements there, which was problematic. And you can see the crawl space and the hospital in the background here. It's still standing, but urban legend says it twisted on its foundation about 2 degrees. Nobody really knows if that's true or not. And I showed you the Home Depot in the other picture, but they're open for business already. And there's a new Home Depot in the upper right over here. And that's the parking lot, asphalt, totally scoured. Most of the damage through there was EF3, EF4 through the city. There were tiny little pockets of EF5 where they saw manhole covers actually lifted up and thrown. Those were pretty heavy things. So that's where it got the 200-mile-an-hour designation. We saw a lot of this too. People writing on the sides of homes. There's the X's again. There was nobody found in that particular house. Nobody was injured or killed, but she obviously lost her mother in the tornado. So yeah, there was a lot of that. And back to Dillon's grocery store. The manager here was like a local hero. He was a local hero because he had a plan. He had 2 weather radios in the store, and as we'll see in a second as I go through this, the weather radios went off twice. There were 2 different warnings that were issued. The first one he kind of ignored, and then he but was kind of attuned to the situation. Second one went off, he got more concerned, went outside to look around, came back in, he had 35 customers, and there were actually a few people in the parking lot. He got them all into the cooler right here. And he held the door personally as the tornado just ripped everything apart around him. So we talked to a lot of businesses, and those that had a lot of survivors in those businesses had a plan. But there was a lot of businesses that didn't. It was just kind of a ad hoc thing where every man for themselves. People leaving stores and calling around for information and not really getting the right stuff. So I find it easier to talk about our service assessment findings and our recommendations in the context of the radar. So what I'll do is I'll step through some of them pretty quickly. A lot of the radar images, if you haven't seen these before, they're pretty interesting. But as we step through in time, I'll kind of highlight some of the findings that kind of correspond with the evolution of the storm here. So this is 5:09 p.m. Central Time. There's actually 2 storms here, Storm A, Storm B, and this is the time they issue the warning for Storm A. They get a report of a funnel cloud and issue the warning for most of Jasper County, which includes Joplin. But Joplin is down here on the southern part of the county right here. This is the eventual tornado path. Joplin has some funky city limits. The airport is actually in the polygon. So the warning mentions northeast Joplin. And weather radio is activated for all of Joplin, all of Jasper County for this warning. And the warning basis indicated, as it should, that the threat is mostly north of Joplin. And that warning that produces some confusion amongst people who hear it about the actual location of the threat. And that was, we found that in a minority of our surveys, about 30%. National Institutes of Standards and Technology, they did their own study of this. It took 2 years. We had 6 weeks. They got 2 years. They found that about 50% of their sample reported confusion due to this warning right here. And this is the first time, this is when sirens were first activated at this point at 5:09. So this is 5:17, and a warning is issued for the second cell, Storm B, which is actually the one that produced the tornado. So NWR EAS activation occurs in Joplin for the second time in 8 minutes. And the emergency manager did not sound the sirens for this, figuring I just did it, I'm not doing it again. So people are hearing on radio and on news reports and on local TV, 2 different warnings going out. So there's still confusion. You know, where is the threat? Is it still to the north of the city? So that turned out to be a bit of a problem for people taking proper action right away. This is the velocity here at also at 5:17. And you can see that the storm in question is right here, and the velocity is range folded, it's compromised. And that was an issue because the Springfield office at the time were using a VCP, a volume coverage pattern, that had a fixed PRF. And our recommendation was, and you can move this range folded area here by changing the pulse repetition frequency. You can move it in or out. And so they could have moved it off of that. This is at a critical warning point, and they didn't do it. They actually issued the warning based on it was a good warning and all, but they issued based on the Tulsa and the Kansas City radars. They did a really good job with the situational awareness, and this is like an early lead time for this warning for Joplin proper. So here, this is at 5:29. This is about 5 minutes from touchdown, and there's a cell merger going on. Movement is taking on a more easterly direction. You're starting to see more supracellular characteristics. The circulation is actually shifting gradually to the south with time. And here's the velocity at that time. Your rotational velocity is 40 knots at this point. Our normalized rotation, which is something that we get in GR2 software. Anything over a 1 is usually indicative of a tornado. And you can see a pretty good circulation right here along the Kansas-Missouri line. Okay, this is 5:34 p.m. This is when the tornado actually touches down this rural area between Galena and Joplin. You can see there's a small hook echo right here. Lead time touchdown is 17 minutes. I've got some video of the touchdown, which I can't show you. It's copyrighted. But I will say that I'm going to show you how dangerous storm chasing can be. There's 2 chase teams out here at this time, and they should be down in here, right? But I think they ended up right here. And I would say that, in looking at the video and looking at this, I would say the probability of them surviving was probably pretty low, but they did. And it was rain wrapped at the time. As you can see, it's pretty moist on this radar image. There was also a TV webcam. It's on a tower here at the local TV station right in here, which actually played a central role in getting people to take shelter. And we'll get to that in another slide here. This is the 5:34 velocity couplet. Rotational velocity is up to 43 knots. This is usually indicative of something of that value. Is indicative of an EF1 to EF2 tornado. And that's some work that I'll show a little bit later from Brian Smith and Rich Thompson at SPC making a relational climatology of rotational velocity to a tornado EF scale. Okay, so this is the major finding of our report, and this was also the major finding of the NIST report. So I felt good about that NIST was able to duplicate our results. with a much larger sample size. But you can see at this point, debris ball is very much evident right here. And you're getting probably EF4 damage, and it's crossing Schiffer-Decker Road, which is the Joplin city limits at that time. And the big finding that we found was that the majority of residents, they weren't ignoring warnings, but they did not take protective action until they processed credible confirmation of the tornado magnitude and their own vulnerability from a high-intensity cue. And there were several high-intensity cues. At this point, when it crosses Schiffer-Decker, the emergency manager for Joplin sounds the sirens again. A little, 17 minutes late, but he sounded them again. And that caught people's attention. They'd heard sirens before. They'd also heard, and a lot of the talks that we did with, a lot of the interviews that we did with people, people said, well, these things go off all the time and nothing happens. And they're right about that. And it was made worse by emergency management. They tested their sirens weekly. So people were really conditioned. They were hearing, like a car alarm. It goes off all the time. After a while, you just ignore it. And so there was a lot of that, which caused people to delay their sheltering actions. And they wouldn't do anything until they got that high intensity cue. And it was the areas that we got that were the sirens being sounded the second time. That was something unusual. The TV stations were watching that webcam. They didn't realize that they were seeing the tornado on the webcam at first, but when they did, which was right about this time right here, they just started going crazy on the air, wall-to-wall coverage, and telling people to take cover. And that's what prompted people to action. And there were also people who were outside that physically could see the tornado moving towards them, and that prompted them to go to action too. A lot of people could see it. It was rain wrapped, but they didn't quite know what it was. And we had several instances of people driving their cars right into it, not realizing, thinking it was a dust storm or something. Very tragic. So low-level intensification is occurring really fast at this point. It's just like it's increasing non-linearly. And the rotational velocity here is 47 knots, and the NROT's up to 1.6. And the way the radar was set up at the time, you get a volume scan every 4 to 5 minutes. And so this was probably our second biggest recommendation right here, was that Weather Service should develop these alternate scan strategies which allow for more continuous sampling near the surface. The FAA TDWR radars, like the one here at Metro Airport, they scan every minute at 0.1 degrees. We developed something called SAILS. Weather Service took this recommendation and jumped on it quickly. And SAILS cuts now produce a half-degree elevation slice every 2 minutes. And that seems to be pretty popular. It seems to be working pretty well too. It just allows us to kind of track the magnitude of these circulations as they occur much better. Okay, this is at 5:43. There was actually at 5:39 there was a follow-up severe weather statement from the Springfield office. And they used, this is just a massive debris ball here, and you can see it on the previous volume scan too. Despite that evidence that something really big was going on, they were just issuing boilerplate wording. They were under a lot of stress, obviously, but their statement looked like any other statement, any other tornado warning. Just your basic, here's a tornado. Nothing to really catch anybody's attention. And so our recommendation here was that forecasters should use enhanced wording that convey a sense of urgency. We weren't conveying that in our products. And that should be used when extremely dangerous situations like this are in progress. They also did for this morning where nothing was happening, they decided at this particular time to issue a follow-up statement for that warning, which was a bad idea because it caused a lot of confusion. It was only in effect for 6 minutes, but when this is going on in the city, you don't want to be talking about what's going on here. They should have just orphaned that. Okay, you can see at 5:43 that you don't see rotational velocities like that very often. That's 100 knots.
Not at 60 miles from the radar.
Yeah, it's gate to gate. So you know something big is going on here. And that debris ball that you saw in the previous image was measured up to 30,000 feet. So it was pulling debris up that high. It was pretty tremendous. It's moving very slow at this point. People were reporting an eye with the tornado, which seems kind of weird, but it was a big tornado, and we have video evidence of that. Some of you may have seen it. We have security camera video from an elementary school, which is somewhere in this area right here, that security camera is actually pointing down the hallway, and you can see damage, debris blowing away from the camera, and then it stops for about 15 seconds. And then it comes flying back at the camera until everything goes dark. So there was definitely something going on there. Okay, and this is at 5:48. This is when things are kind of wrapping up a little bit. It's mostly through the city, and they issued another tornado warning to replace these two. And you can kind of see the stress that the office is under. Putting out a big warning which covers both of those cells. And that's a tremendous debris ball right there. On this particular warning, they did use enhanced wording. So this is where the tornado crosses Range Line Road and impacts those big box stores. Almost all of the fatalities occurred from this point to this point right here. Very few outside of that range. Some people said that the weather enterprise failed in this. Well, I don't agree with that. I think that some things could have gone better, but some things went well, and I think a lot of lives were saved by this particular warning right here. The initial touchdown lead time was 17 minutes. That warning went out 21 minutes before it hit the city limits, 26 minutes before hitting the high school, and almost a half an hour before hitting the big box stores over there on Range Line Road. They were using multiple radars. They could have managed their range folding a little bit better. They recognized the impending cell merger, which caused them to issue this particular warning right here to the south of that one. And you can see that the polygon actually pretty accurately, the path of the tornado is right down the middle. And in my opinion, this is the single most important factor in saving lives, was the issuance of that warning. It was skillful, and the polygon was accurate. Not that there weren't things that we could improve on, and we had several recommendations along those lines. These are our key findings, which I went through most of them. I want to hit these two in green a little bit harder here, which I didn't really cover. We found that the sirens and the warnings themselves had lost a degree of credibility amongst the residents of Joplin. First of all, the sirens are ambiguous. They go off, you don't necessarily know what they're for. And in Joplin, the emergency manager would issue them for severe thunderstorm warnings as well. And so we heard a lot of talk about they go off all the time and nothing happens. People are forced to seek additional information when a siren goes off because you don't know what it's for, how long it's for, where it's for. You just hear it. They're designed for outdoors. But the vast majority of people, that's how they got their information first. 90% of the people that we interviewed said, first I knew about this is I heard the sirens going off. So credibility was an issue. And false alarms were an issue. Because they're right, the 76% of our warnings in totality are false alarms or tornado warnings. That's pretty high. So as service assessments go, this recommendation was pretty bold. And in fact, I'm a little surprised that it survived, but it did. We jumped right out there and took a risk and said, we need to change the way we do tornado warnings. And so this is the recommendation that we need to explore evolving the warning system. We didn't recommend turning it over upside down. That was the response we got when we proposed this IVW experiment, but we wanted to gradually move forward. We want to better support effective decision making. We need to utilize a simple impact-based tiered warning information structure, something that promotes warning credibility, empowers individuals to make appropriate decisions in extreme conditions. And these are related to our findings right here. We want to get people to take shelter more quickly instead of searching for information for too long. We want that high intensity cue, I call it a non-routine mechanism here, the high intensity cue in our warning that prompts people to take immediate life-saving action in these extreme events. We want things to be more impact-based for clarity when people do their personal risk assessments. compatible with our operational capabilities and technology, compatible with emerging mobile communications technology, and easily understood, obviously. Our probability of detection for large tornadoes is actually pretty good. For EF3 plus, it's like 95%. But our problem is the perception of false alarms and the actual false alarms impact our credibility, and we need to fix that. We're kind of basing this on what we think is our societal needs. At least in my opinion, these are the societal needs. They demand that warnings emphasize high risk, high impact events and minimize false alarms. And this is your basic risk paradigm right here. There's 100 more like this. I adapted this from Cordoba et al. In 2012. But risk is a function of hazard character, exposure to the hazard, and vulnerability to the hazard. And what we've tried to focus on is the expected magnitude and intensity, which are missing in tornado warnings, or we're missing in tornado warnings. In fact, tornado warnings are the only hazard that we issue warnings for that we don't indicate what the expected magnitude is. And I can't tell you in all of our interviews that we were out there in the field sifting through rubble with survivors, and they were very gracious. Only one person turned us down for an interview, but we'd sit on their steps with their house gone behind them. And you'd frequently hear, "I didn't know it was going to be this bad." And which is a natural tendency, I think. So we want to actually, we have the capacity to do this, to actually put that information into a warning as a high intensity cue when we need to. So this is our initial step, impact-based warnings, which we're now doing in all the offices in NWS Central Region and Southern Region right now, a few of them in Eastern Region and Western Region. This was our, we're trying to meet this recommendation that we put forward in the Joplin assessment. Our intended outcomes is we want to reframe the warning problem and message in terms of societal needs. When we wrote this was in like 2011. The previous 5 years, over 3,000 tornadoes occurred. 87% of those were EF 0 and 1, which resulted in just 3% of the fatalities. They were all from EF 1. In fact, the mortality rate from EF 0 tornadoes and EF 1 tornadoes is the same or even slightly less than severe thunderstorm winds. On the other hand, the remaining tornadoes, the 13% that are EF 2 to EF 5, result in 97% of the tornadoes, or tornado fatalities. So this is what we're trying to do. You can increase the fidelity of your warnings by distinguishing situational urgency by better emphasizing these high impact events. We're just trying to we're not trying to do away with tornado warnings for all tornadoes, but we want to ring the bell a little bit louder for these high impact events. And we can incrementally do that, which is what we're trying to do, and I'll actually show you that, and conduct an initial proof of concept, which we did. So these are the considerations for improving the warning system. Communication of risk is the key, and that's the prime public warning challenge for rapid onset events. People have an optimism bias. They think, they're out there, it's not going to happen to me. So it's a challenge to convert this perception of safety to a perception of risk. And like I mentioned, we don't want people to drag their feet when it comes to finding shelter. We don't want them chasing around for information. We'll just keep searching and searching. So, and people, of course, as I've talked about, need clarity on potential impacts. How does this affect me? How bad is it going to be? And then the credibility of the warning is key. It's actually the most important commodity for effective risk communication. When you have warnings from multiple sources, Weather Service, private sector, media, that causes confusion. So you want to get consistency of messages from multiple sources. And of course, the perceived accuracy of the warnings is important. We're pretty good here. We're not good there. So this is what an impact-based warning looks like. This was for the Rochelle-Fairdale tornado in northern Illinois early April, I think it was. April 9th. So this is we call this an enhanced warning. This is what we think. We think an EF2 to EF5 tornado is going to occur. And you can see right off the bat here, a high intensity cue. It's a particularly dangerous situation. You don't see that in a regular or legacy tornado warning. We got the hazard, and then we're actually stating the impact. Again, we're restating it's a life-threatening situation. These are the impacts that could occur. Flying debris, if you're caught without shelter, mobile homes destroyed, considerable damage to homes, businesses, and vehicles, complete destruction possible. Just to tell people this is what you can expect from this particular tornado. And then here's the locations, of course, and then we're repeating large and dangerous tornadoes on the ground and giving calls to action at the bottom. And then the third thing, this is new at the bottom, is we have these tags for hail and tornado. These are designed to be compliant with common alert protocols from FEMA. And part of the CAP, common alert protocols, are that you mention the magnitude of the hazard in there. And in this case, you can see that we have a tornado damage threat that's considerable, which is designed to raise people's awareness of the threat in situations like this. This was an EF4 tornado that pretty much destroyed the town of Faraday. So I'm coming up to the end here finally. This is some of the verification statistics we've done over 3 years. Like I said, we've done this for 3 years in several locations, 2 years in all of the central region offices. And so we're able to take a look at this and see how we're doing and see what kind of skill we have and how we can leverage this information to improve our warnings. Like always, our base tier warnings, which is like our legacy warnings, these are for small tornadoes, EF0s and 1s. Those warnings are still dominated by false alarms. 69% or worse. The elevated tier warnings, on the other hand, is a little bit different. Those are marked by tornado occurrence. 67% of those warnings have a tornado of some size, and a plurality, easy for me to say, of those are EF2 to EF5, 46%, majority being EF1 to 5. So we are doing a pretty decent job of identifying these larger events. And if nothing else, our elevated tier warnings are a confidence marker that a tornado is going to occur. Now those are from a warning perspective. From an event perspective, when an EF0 or EF1 tornado occurs, it's mostly unwarned. Or more precisely, it's an unwarned EF0. Those outnumber EF1 events by a factor of 2. So if you're trying to make a living on this, which we have been, most of your base tier warnings are dominated by false alarms. Nothing happens when you issue them. And when an EF0 to 1 tornado occurs, most of the time there's no warning with it. That's a tough way to make a living. So on the other hand, base tier warnings a little bit different. I talked about this. There's very few false alarms with those, only 33%. In addition, very few EF2 to 5 tornadoes are unwarned, only 10%. So that's pretty good. You get a probability of detection of over 90%, and you get your false alarm rate down to 33 for those elevated tier warnings. One of the problems that we have is that the majority of these EF2 to 5 tornadoes are still covered by base tier warnings. Forecasters are underutilizing it right now. And granted, it's new, we just started, but we could issue more of those. So the bottom line is that the IBW warning framework seems to have value above that provided by the legacy warning system. In terms of our stated goals, we want to provide a basis for communicating elevated risk and limiting false alarms for large tornadoes. This is a study by Smith and Thompson that I referenced earlier, and this is down here at the bottom, you've got EF scale. This is actually null events, no tornado events here, EF zeros, 1, 2, 3s, and 4s. And this is the rotational velocity at the half-degree level. And you can see where we can have skill in this area by looking at half-degree peak rotational velocities. There's a minimal amount of skill distinguishing between EF1s and EF2s. You see there's overlap between 3 of the 4 quartiles there. Same thing if you try to distinguish between adjacent EF scales, the same kind of thing here. You got a lot of overlap. But if you start moving out a little bit, you can see that all 4 quartiles are separated here between EF0s and EF3s. So there's a strong signal there allowing you to separate larger tornadoes from small tornadoes. And you basically have no hope of distinguishing no tornado from a small tornado. There's no skill in that at all. So this is kind of the basis, of keeping our forecasts accurate, our warnings accurate. And we're doing some more work on that. And bringing it full circle to my last slide, to this room right here, Where's Trent? There he is. This is Trent's master's project from last year, comparing, this is the time evolution of rotational velocity at several elevation slices. There's actually a little bit of information on the diameter of the circulation. And this, of course, right here this is time, of course, and this is the EF scale. So this is getting a lot of play in the Weather Service right now. Just started with it. There's a lot more work to do, but this is pretty good stuff. So there you have it. Any questions?
When we think about the life cycle of pollen, the tree emits pollen to try to transmit its genetic material. So it emits these huge amounts of pollen grains with the small chance that one of those grains might land on a tree somewhere else.